very fine work on multi-user channels and their capacities in the failing context. Since this year he's been at the University of Minneapolis. His research interests are in multi-user systems, including ad hoc networks and sensor networks. And today he's going to talk about capacity results for multiple antenna channels, largely for the downlink.
Yeah, largely for the downlink. Yeah. Thank you, Sam. Thank you for having me there. Thanks for coming. So as Dr. Narayan mentioned, I'm going to be talking about the capacity results for MIMO multi-user channels, but in particular I'll focus on the downlink channel, but I will talk a little bit about the uplink channel and the connection between the downlink and the uplink channel. And just like to acknowledge collaborated on this work, Sri Ram Vishwanath, my advisor at Stanford, Andrea Goldsmith, Syed Jafar, Wan Bangri. Okay, so first, just an outline, I'll start with the system model, which will show you the downlink and uplink channel, and then move on to the idea of dirty paper coding. So this will give us an achievable region for the BC, which is the downlink or broadcast channel. And then we'll be able to talk about the sum capacity of this downlink channel, and then which is achieved using dirty paper coding. And then I'll do a comparison between this optimal dirty paper coding technique and time division multiple access. This section I have a feeling we won't be able to get to, but this is just some algorithmic work we've done regarding capacity and some conclusions. So first off, the basic model we're motivated by is the standard single cell model. So we have a base station here in a cellular system, for instance, or an access point in a wireless LAN atmosphere where we have a base station communicating with multiple mobile devices. And there are really two relevant channels here. One is the downlink or broadcast channel. So this is the channel from the base station to the mobiles. And broadcast channel is the information theoretic term here, but notice this is the base station has independent message for each mobile. So this is not a TV or radio broadcast. And the reciprocal channel is the uplink channel, or multiple access channel, in which each of the mobiles has a different message to transmit to the base station. Okay? So what we're interested in are looking at these systems with multiple antennas at the base station and possibly at the mobiles, and getting some capacity results here. So we're going to be studying channel capacity, which is, just quickly overview, is set of all simultaneously achievable data rates. Right? In a point-to-point link, channel capacity is a single number, which gives you the kind of fundamental upper bound on reliable communication. We look at a multi-user channel, for instance, the channel from this base to two receivers. And we now have a capacity region. We have a two-dimensional capacity region. It tells us we could transmit only to user 1 at this point here, or only to user 2 at this point, or simultaneously to both users at any point in this capacity region. Okay. And the motivation is, of course, this gives us limits on fundamental limits on performance of any system, and hopefully it also will motivate some practical transmission strategies. So if you just look at channel capacity and from the network performance, capacity really tells you how well you can do at this physical and math layer, right? How big of a bit pipe, for instance, in a cellular network do you have at the end of your network? And once you know this, then you can consider higher layer issues such as scheduling, routing, etc. on top of these capacities. Once you know kind of those fundamental limits of your physical layer. And it should be noted, of course, capacity results are all without any delay constraints or without any complexity constraints. Okay, so we're going to be talking about MIMO. Just a quick slide about standard MIMO. I'm sure most of you, or almost all of you, are familiar with this. Here's just a picture of a point-to-point MIMO system where we have 3 transmit antennas and 3 receive antennas. And we can put all these gains, HIJs, which are for each of the transmit receive pairs, into a big matrix H. And we get the standard mathematical model with additive Gaussian noise in it. So the output Y equals HX plus N, the independent Gaussian noise. But this is for the point-to-point case. We're interested in, of course, the multi-user case. So we have a base station here with M antennas communicating with K receivers, and these K receivers may or may not have multiple antennas. Really, I'll talk a lot about the case where these receivers only have single antennas, but all these results generalize to the multiple receive antenna case as well. And MIMO is actually being proposed for a number of future systems. 802.11n, which is the next generation wireless LAN standard, 802.16 also are looking at using MIMO in this kind of information, or in more of a blast format instead of just for diversity. And so this is a very relevant model to be studying. Okay, here's the precise mathematical model. We have a input vector x, which is our MI1 input, which goes to a different channel, HI. This is a system model for the downlink channel only. this X goes to a different channel for each of the K users. So we have a different channel, H1 through HK for the K users, and we have additive Gaussian noise. Okay, so the received signal at the ith receiver is just HIX plus NI. The additive Gaussian noise assumed to be independent, uncorrelated across antennas. Okay, so our channel H is now a row vector. Notice this is for the single receive antenna case, but this is not really a limitation, but just for simplicity, we'll talk about the single receive case. So each HI is a row vector, and we can concatenate these channels if we want to look at the entire system. And we're going to look transmit power constraint P, which means just the expected value of the norm of the channel is constrained to be less than P. Standard assumption on Gaussian noise. And one key thing to notice is that we're going to be looking at non-fading channels. So the channel is fixed and is known at both the transmitter and at all receivers. And this is actually a very important assumption for the broadcast channel, for the broadcast channel. Okay, so what we're interested in is finding the capacity region of this channel here, where we have multiple antennas. But to start off with, let's just go over the single antenna broadcast channel capacity results. Okay, and we'll see why we can't generalize those to the MIMO context in a very straightforward way. So here we have a single antenna broadcast channel. Input X here. Channel gains are H1 and H2, just scalar quantities, just complex quantities here. Y1 is just a scaled version of the input plus Gaussian noise. And what is optimal here? Okay? This is the channel first looked at by Kober and proved the Gaussian channel was, the capacity region was found by Bergmans. And what is optimal is just to simply choose separate Gaussian code words for each receiver. So a code word X1 is generated, which is intended for receiver 1. A code word X2 is generated, which is intended for receiver 2. And this is done independently, so we use, for capacity achieving codes, we use just random codes. And all the transmitter does is transmit the sum of the code words here. So we just take this X1, which would really be a vector in time, maybe a length n code. We just add it to the length n code for user 2 and simply transmit the sum of these two code words. And basically, we leave the receivers to do the decoding, kind of take care of this sum. And what we do to achieve capacity is we use successive interference cancellation. So let's assume that H1 is larger than H2 in norm. This really makes this channel degraded, which means that the signal of user 1 is strictly better than this signal at user 2. Okay. What this allows us to do is that user 1 can actually decode out X2 before decoding X1. Okay, so Y1 here is the sum of X1 plus X2 plus noise. And the idea is that X2 is, by assumption, decodable at Y2. For any design code, of course, we want X2 to be decodable at receiver 2. And anything that's decodable at receiver 2 is also decodable at receiver 1, because this is a stronger signal, statistically speaking. So receiver 1 decodes out X2, subtracts it out, and this just leaves a clean channel between the base and receiver 1. Okay, and then receiver 1 decodes X1, its own channel.
This H1 is fixed for the entire
Yeah,
transmission?
so right now H1 is fixed.
For the entire transmission?
Yeah.
One constant?
H1 is, yeah, H1 and H2 are both fixed for all transmissions here.
So what happens if H1 is equal to H2?
You can actually choose, it's the same argument holds, and either of them can do the successive interference cancellation, actually.
Wasn't the argument based on the fact that one was, you said,
It doesn't actually have to be strictly better, it just has to be greater than or equal to kind of argument, yeah. And I should mention that receiver 2 isn't able to do this successive interference cancellation. He has a poor channel, so he's not able to decode out X1 before decoding out his own signal. So what he does is just treat X1 as an additional source of noise. X1 is seen also for the capacity achieving scheme, so this is just an extra source of noise. So any power you put into X1 just reduces the rate of user 2. And so just a picture of what the capacity region looks like. Here I've assumed that H1 is larger than H2. This is actually in power. So what receiver 1 is doing here is canceling out the code word for receiver 2, that X2 signal, and then decoding his own. So the capacity region is given by this blue curve here. Of course, the endpoints correspond to the point-to-point capacity. So if we transmit only to receiver 1, we get the point-to-point capacity from base to receiver 1. Similarly, up here. Okay, so notice that this region is strictly curved, and it's strictly larger than what you could get by doing time division. It's strictly larger than what you could do by any really orthogonal method of transmitting. Time division, frequency division, CDMA. Right? And this is capacity achieving channel. So, as I mentioned, receiver 2 just treats X1 as an extra source of noise. So, the way you trace out this curve here is by varying up the amount of power you put in X1 and X2. Okay, so for single antenna broadcast channel, what's optimal is simply to transfer the sum of code words. We just use single user point-to-point codes, Gaussian codes, and we transfer the sum of these codes, and then we do successive decoding at the stronger user. And this generalizes to more than 2 users. Right? So, as you said before, the stronger user, in this case the stronger user would be 2. He decodes out the signal intended for this receiver first, to give himself a clean channel. Now let's see if we can generalize this or extend this to the MIMO case. And the basic problem is that we cannot naturally use the successive decoding technique in the multiple antenna broadcast channel. And this is really intuitively seen by just considering the simple 2 transmit antenna, single receive antenna example. So let's say H1 is 1, 0.5, say 2 by 1 row. H2 is the flip version of this, 0.51. It's obvious that there's no ordering between the two. You can't say H1 is bigger than H2, you can't say H2 is bigger than H1. So, which means you can't say receiver 1 can automatically decode something that receiver 2 can decode, or vice versa. This is why I say there's no natural successive decoding. You could kind of enforce this on your system. You could, for instance, communicate the receiver 2 at a very low rate, so that receiver 1 can also decode. But there's no natural successive decoding. In the scalar case, it's a very natural thing. This was without doing anything, without altering your coding scheme, the better receiver could automatically decode anything the worse receiver could do. Okay, so successive decoding is very natural there. Whereas in MIMO, there's no such natural, there's no full ordering on. Right? So we have to do something else. And this is where the idea of dirty paper coding comes in. So instead of doing receiver cancellation, we're actually going to pre-cancel this interference at the transmitter using this idea of dirty paper coding. So dirty paper is, we're going to use it for the MIMO case, but in fact, it's actually an alternative way to achieve capacity for the single antenna broadcast channel as well. And the difference is that the transmitter really does the pre-subtraction, or does kind of the hard work in this interference cancellation. Okay. So this problem was first considered by Costa, I believe, in the early 80s. Then it didn't really have much practical significance, and it really come to life because of this broadcast channel. So the problem that Costa looked at, the output Y equals the input X plus S, which is this additive interference term, plus our standard Gaussian noise. So X is our transmitted signal, S is this additive interference. So clearly, if the receiver knows S, this additive term, capacity is unaffected by S. The receiver simply subtracts out S from whatever it receives, and there's no problem with the additive interference. It has no effect at all. But the question Costa looked at is what happens if only the transmitter knows S? So the transmitter knows S, but the receiver does not know S at all. And what he found was very surprising, is that capacity is still unaffected by S in this case. What that means is that the transmitter can somehow efficiently pre-subtract S. Okay, there is a method for efficiently pre-subtracting S at the transmitter. His idea was quite theoretical, dealt with random Gaussian codes. It was actually a nice, much more practical scheme, which I'll go over now, of how to do this pre-subtraction. So let's look, and this is based on a modulo operation. So let's just look at a noiseless example. The noise doesn't really affect the strategy here. Let's say our output Y is just X plus this additive interference. And let's say that you want to send U, some signal U, which is between -1 and 1. So this fact that it's U, or the signal that we want to transmit, is in a bounded interval is important. And what we're going to do is something really just like Tomlinson Harshimmer recoding for ISI, which many of you may be familiar with. Okay. So the idea is that I want to transmit U, which is 0.5, and there's some additive interference, S. I just assumed S is 3.75 there in this case. So the naive thing to do, of course, would be to simply transmit U minus S. It seems like it works, and it would let you receive U at the other end without any problem, except, of course, S can be very large, and this could use up all your power. Perhaps you can't even subtract S while maintaining your power constraint. Okay. But let's use the fact that U must lie in this -1, 1 interval. And notice that, and have the receiver do modulation, modulo negative 1, 1 on whatever it receives. So it receives a signal y, and then it performs a modulo operation. Okay. If the receiver is performing this modulo operation, if y is 0.5, or 2.5, or 4.5, or any of these red dots, okay, after the modulo operation, it's going to become 0.5. Right? All these red points, modulo this negative 1, 1 region, get reduced down to 0.5. And the receiver will know what you intended to send. Okay? So instead of sending the difference between u minus s, okay, you actually send the difference between the closest, you find the closest red dot to this blue dot, to the additive interference. Okay? And you send something so that what the receiver gets is this red dot, okay, which will be modulo down to the intended signal. So what you send is actually 0.75 because the ultimate received signal will be 4.5, and I just send the difference between those two. And this is actually just u minus s modulo that region. Okay. So this is the pre-coding in one dimension. In fact, for dirty paper coding, we need to do it in higher dimensions. This is the picture for a two-dimensional signal. So I want to send u, which is a 2D vector, which u is some vector that lies in this region here, this hexagon, and s is some arbitrary random interference, this blue dot here. Again, I could send u minus s, but this would just take too much power. So I noticed that instead of receiving u, if the receiver receives any of these red dots, they're all equivalent. Once the receiver does this modulo operation on this unit here. Okay, so I do the same thing. I choose the closest red dot to the blue dot, so the closest representation of my desired signal, and I transfer the difference. Okay, so I transmit x here. Okay, and this scheme was designed by Erez Zamir Shmai a couple of years back. And the idea is, though, the problem with even 1D pre-coding, which is done for ISI channels, is there's a shaping loss, because I must make u lie in this interval between negative 1 and 1. This is not optimal for a Gaussian channel, right? And we take a loss for this reason. And the way to overcome this is by doing this dirty paper coding in higher infinite dimensions. Okay? So if I do this dirty paper coding in infinite dimensions, you eliminate the shaping loss, okay? And you completely losslessly eliminate s. So there's no effect of s if you do this dirty paper coding technique in high enough dimension, okay, or in infinite dimension. Okay, now we're going to see how this applies to the broadcast channel. And please interrupt. Are there any questions? Yeah.
So doesn't S need to be stronger than some?
No, even if S was something like this, then it's even easier. For instance, if S is actually, let's say it's a vector right here, you can just transmit u minus S, and you may not even need that modulo operation. The power of S doesn't matter actually. Yeah. And S the distribution doesn't even make a difference if we're using this scheme.
What kind of signal is considered interference? Besides noise, what is interference?
So we'll see right now, in a multi-user case, interference will be x1. And this will be what I want to send to receiver 2.
Yeah, I know, but what? So the signal to the message to other users will be the interference.
Yes. Yeah.
Right.
Yeah. So this is actually not a very, in kosher setup actually, this S actually needs to be known non-causally at the transmitter. Okay, this seems very unnatural. So if you're coding over block lengths of 10,000, you need to know S for the next 10,000 channel uses, okay, which is unnatural in practice. But for the broadcast channel, we'll see it doesn't make a difference. Anything else? So let's go on and see how we use this for the broadcast channel. So this coding scheme was, dirty paper coding was first adapted by Kyra Shmai a couple of years back. Okay. And the idea is we pick a code word for user 1, so x1. So this is a length n vector. So I pick a length n code word for user 1. And then I just treat x1 as interference for user 2. Okay. And I employ this dirty paper coding scheme, okay, while I'm choosing the signal for user 2. Okay. And then what receiver 2 does is performs this modulo operation, and that essentially eliminates x1 from the picture. It's as if, to receiver 2, it's as if x1 didn't exist. Okay, because this dirty paper coding will perfectly cancel out this additive interference, which is x1. I'll show you that picture again, the 2D picture again. But user 1 doesn't get the benefit of this DPC. It can't work both ways. So what user 1 does is just treat x2 as an extra source of noise. Okay, so instead of sending just the sum of x1 and x2, we're going to do this DPC operation in between. And notice that I just arbitrarily picked user 1 to go first. I could have switched the order here. Unlike successive decoding, there was no requirement that user 1 channel be better than user 2 channel or vice versa. So let me just show you that picture. So before this was S. This is now x1. So this is a length 2 code word, for instance, here. And U2 is what I want to send, or what I want receiver 2 to receive. But instead of just sending the sum of this and this, I send this. Okay. And then once receiver 2 does the modulo operation on its receive signal, it can determine that U2 was actually what I desired to send. Okay. So, but remember that x1 was chosen first, so he doesn't get any of the benefit of this interference cancellation. Okay, so if you want to see the rates that are achievable, the specific equation isn't so important, but what happens if I do this, if I choose x2 second, is that receiver 2 experiences no interference. Okay, he does this modulo operation, this eliminates x1 from the picture, and you get basically a clear channel from the base to receiver 2. So the rate of user 2 is given by this log net expression here. So sigma 2 here is the covariance, the spatial covariance of x2. Okay. And on the other hand, receiver 1, the rate of receiver 1 is affected by sigma 2, or by x2. Okay, because user 1 doesn't get the benefit of this DPC operation. User 1 just has to treat x2 as noise, extra Gaussian noise. Okay, so that's why you see sigma 2 here. So then if we consider all possible spatial covariances, so in the single user case, we don't need to look at powers between x1 and x2, because we have multiple transmit antennas, we have to do some spatial correlation between what's transmitted on each antenna. So x1 has a covariance structure and x2 has a covariance. So if we consider all covariances that meet our power constraint, that power constraint P ends up being this trace constraint, we get, for every sigma 1 and sigma 2, we get a different set of rates that are possible. If we encode in one order, we get this one. We get this R1, R2 pair. That's if we encode receiver 2 second and give them the benefit of this DPC. And if we do it in the opposite order, we get this rate pair, this R1, R2. So then consider all possible sigma 1, sigma 2s that meet the power constraint. These also have to be positive semi-definite. And you get an achievable region for this broadcast channel. Okay. And this is actually equal to the capacity region for the scalar case. It's easy to see. In the scalar case, though, you only need one of the two orders, actually. So here I've shown either user 1 or user 2 can go first. In the scalar case, the best user should always get the benefit of that DPC operation. And this is strictly larger than successive decoding. So I mentioned before, I could do successive decoding. I can do interference cancellation in a MIMO broadcast channel, but I'm going to have to put some artificial limits on the rates, just so this interference cancellation works. Okay, you'll be much better off doing this dirty paper coding instead. Okay, so now we've seen, first off, let me just give you a beamforming interpretation. So if we have multiple transmit antennas and single receive antennas, let's say you're doing SDMA, space division multiple access, which is, I guess, I would say a more practical, or perhaps a practical scheme for multiple transmit antenna broadcast channels. What you do with SDMA is you choose beamforming directions V1 and V2. Okay. Then you choose scalar code words for each of the two users. You choose some scalar code word X1, another scalar code word X2. And then you simply transmit V1 X1, so you multiply X1 by the beamformer, and V2 X2. Just a naive sum of those two. Right. And then you don't do any interference cancellation at the receiver. So receiver 1 tries to decode X1, treating this term as noise. Receiver 2 tries to decode X2, treating this term as noise. Right. There's no interference cancellation for either user in this case. What you do with DPC, if you're using DPC, is you do the same thing. You choose beamforming directions V1 and V2. These are like choosing covariance matrices sigma 1 and sigma 2. And you just transmit what I call the DPC sum of V1 X1 and V2 X2. So instead of transmitting this naive sum, you basically transmit the DPC sum of these two. You do this DPC operation. For instance, you first pick X1, then you basically pick this V2 X2, or you pick X2, kind of knowing what X1 is going to be. Okay, so that there's no interference at receiver 2. And what this does is reduces interference at one of the two receivers. Right? Only one of the two gets the benefit of DPC. Yeah.
This result holds even if I choose the two directions to be orthogonal from the beginning. I mean the two beamformers to be orthogonal.
So even if the beamformers are orthogonal, you're not guaranteed you don't get any interference. Right. So let's say let's say V1 is orthogonal to H2.
Okay.
Maybe that's what you mean. So if we do something like 0, 4, choose V1 orthogonal to H2, choose V2 orthogonal to H1. In that case, you don't need to use DPC. Right? You don't have any multi-user interference. Okay. And something like that is possible. So that eliminates all multi-user interference, but it's not actually optimal. Okay. Basically, you're forcing yourself. Let's say H2. You're forcing yourself to choose V1 to be orthogonal to H2, and this is going to limit your SNR essentially. It's going to reduce all multi-user. It's going to eliminate all interference, but it's not worth it to do that in general. Yeah.
Would you gain anything if you were to send X1 say over a combination of V1 and V2 over two directions instead of sending each of them?
I mean, you could think of it. It does whatever direction you're sending it as. It's a direction. This is just an arbitrary direction. I mean, you can basically. I'm saying you can optimize V1 and V2 here.
So what I'm trying to ask is, can we use both? Say V1 and V2 are orthogonal dimensions.
Okay.
Can we use for X1 and X2 both of X1 and X2 two dimensions instead of just using one for each of them? I know it doesn't lie along the SDMA lines, but maybe as a different coding strategy.
Repeat the question, please.
So you're saying, can we send X1 over
Over,
both
say,
V1 and V2?
Yeah, and so it's X2 also. So
Well,
send, for example, X1 over alpha V1 plus beta V2 and X2 over some other combination.
So if you send X1 over alpha V1 plus beta V2, it's just like sending it in some other direction. It just corresponds to a different, like V1, V2 in this setup here. It's just a different beamformer, basically. For instance, if, let's say V1 is 1, 0 in a two-dimensional case, and V2 was 0, 1, right? That's one set of beamformers. That's one choice of V1 and V2. I could choose my V1 to be alpha, beta instead. Right? It will still kind of fall into this SDMA. I hope that's...
What's the relationship between the number of code words and the number of vectors?
The number of code words.
The number of, let's say, users better, and the number of allowed in directions that you have.
So, no, with SDMA...
If the number of directions is bigger, it will be better, right?
It's going to depend on the channels of each of the users, though. It's not, there's no direct kind of correspondence.
If I had two users,
Yeah.
and 4 possible in directions, I can do better, right?
I don't believe so. You just need to use two. If you have two users and you're just treating all interference as noise.
Like with two independent DPC, and then when I combine, I'll kill more.
Oh, you're saying to do?
Yeah.
No. Okay. See, the problem with the DPC is that you can't get both things at once. So you have to choose somebody first, basically, right? Is that maybe I'm not getting the
Well,
question?
I can do it one way, and I can do it another way.
Okay, well, how are those two different layers of? So I guess the proposed thing is to do DPC on kind of one layer of codes in one direction, help out user one, and then help out user two in another set. But how would those interfere with each other? That's the problem. They will interfere with each other.
Yeah, I just combine the results at the end. After I get the result.
Okay, but you won't do as well though, because what you're proposing is to use two different layers, basically, right? Now, if those layers are independent, they're going to cause when you try to decode layer one, essentially you're going to get independence from layer, or you're going to get interference from layer two.
I will have two identical collocated systems. In the one I do it one way, and the other I do it the other way.
Okay,
All at the same time.
but are they in the same frequency, time?
Everything the same. I just do it different ways.
No, but you're not going to get any benefit from something like that. I mean, you could time share, for instance, between doing it in different directions, and you actually do have to do that. And so,
Sure, because I'm basically playing with some complexity there, and I can go to any.
yeah. So the reason we get back here is you actually I should have put a convex operation here. You do a convex halt, which you achieve using time sharing generally, though, not by simultaneously doing both.
One question. On the next one, the DPC order is up to you,
Yeah.
and you choose V1, V2, right? Now suppose I wanted to maximize the sum rate. Are there any prescriptions for what needs to be done?
So there actually, it doesn't make a difference what order you want to choose. we'll see. I'll try to show a slide and illustrate that. Yeah. Any order, any encoding order will achieve some rate capacity for you actually. Okay. It's not. They will. If you're not only interested in some rate, though, it does make a difference.
Sure.
Yeah. Let me see if the next slide will.
So I have another question with respect to the actual BTC, right? Okay. Most of the results I've seen are all with Gaussian statistics.
Yeah.
And then the actual modular operation you do. So can you tell us anything about what is known when I don't have Gaussian statistics and when I'm allowed to change the modulation, the modular operation?
What do you mean? Do you mean non-Gaussian noise?
Well, that paper coding, what I mean by dirty, I can change it, right? Exactly the specifics. When you put the modular operation together, it's going to be different modular operation. So what's optimal, what's non-optimal,
Okay. So
what's
we go back
against Gaussian, what's not non-Gaussian, just for the benefit of other people.
Okay. So basically, what you want in 2 dimensions, this hexagon is nice because it's the best shape, basically. Right? This is like doing dirty paper encoding or pre-coding is like doing vector quantization. Basically. What you want to do is choose a very good vector quantizer. Okay, because you don't know where S is going to lie, but you want to be able to efficiently. You want this modular region to be big, so you can transmit. You can get a high rate if you're allowed to choose any point in this modular region, right? But you want it to be well spaced in space. So I'll mention this, not the specifics of this, but so effectively what you do then is, if you want to do this in very high dimension, is you're doing very high dimensional vector quantization, which is a complex problem. And that's why dirty paper coding is not necessarily the most practical transmission scheme.
And then the Gaussian assumption?
So the Gaussian noise assumption. Okay.
Because there is a way to do it without actually assuming. Because if you take a partition's point of view, which is what you just said, then I don't have to make a Gaussian assumption. I can study completely non-parametric just by studying properties of partitions, right?
Yeah, I think the Gaussian noise assumption is not. You should be able to reduce by doing this modulo scheme. You should be able to eliminate.
You're not going to get the beautiful formula you have next page.
Yeah.
But you can get.
Yeah. You should still be able to eliminate interference even if the noise is non-Gaussian. Yeah. And there's been some work for dirty paper coding with non-Gaussian noise.
Right.
So Costa's original formulation did require Gaussian noise, but this modulo scheme is, and some other work in recent years has looked at non-Gaussian noise.
Did you run into problems of high low signal-to-noise ratios where the signals will look different?
So I've actually cheated a little bit, and so there's actually, you don't actually completely cancel out the interference in general. You actually trade off some canceling the interference for allowing a little extra noise here. I haven't added that here just for simplicity's sake. But essentially at high SNR, you do completely cancel out the interference.
No, I meant in the non-Gaussian case, then you run into different problems.
I think in the limit you should be okay in general. The noise only comes into place because it basically gets wrapped around in this modular region. So instead of having Gaussian noise over all space, you have Gaussian noise. You take the PDF of Gaussian noise, but then if it goes outside of this, it kind of shows up again.
But the input distribution is not necessarily Gaussian, right? At optimality. So the input distribution, it actually has a discrete support.
No, the input distribution is Gaussian.
The additive noise is not Gaussian.
Okay, the additive Gaussian
That's
noise.
what I meant.
Okay.
Then it's a different story altogether.
All I'm saying is that I believe this DPC operation can be done.
Yeah, sure.
This scheme can be done.
Sure.
This will have other implications if the Gaussian noise is not Gaussian. Okay, but this basic scheme can be done if you have different additive noise with fixed channels, constant channels. Yeah. Anything else? Okay, so we went over this. Let me just show you a slide, of actually what the region looks like. I'll have to draw on this, so you can ignore these captions for now. But basically, if you do DPC, so this is R1 and R2 on the axis, and this is the entire DPC achievable region in the blue curve. Okay. But if I do it in one order, if I let user 2 get the benefit of DPC, so user 2 gets encoded second, the rates I can achieve using DPC are given by something that looks like this. It's strictly smaller than the capacity region, right? It basically gets it kind of gets the left half of this capacity region. Okay, and it ends here. So if you look carefully, this is straight hair. This portion is straight. So I can I get these rates if I encode in one direction. If I help out user 1, I get rates that look like this. I basically get the right half. Okay. And then I need the timeshare between the two to get this straight line segment. Okay. So I can't just do this naive DPC, for instance, to get this point. I can't encode in just one direction. I need to kind of operate at this rate point where I help out user 2 for some fraction, and then I operate at this rate point, and then I can timeshare to go anywhere along this line. So, and if you did something like SDMA, even if you do the convex hull, in general you're going to get something smaller. I mean, you're going to get something that has the same endpoints, but will be smaller. And even doing SDMA in general is mathematically very difficult to. There aren't any really nice techniques to find the bounds of using something like SDMA. So not using DPC. But I'll briefly mention some comparisons between DPC and SDMA, and I'll talk about DPC versus TDMA in a few minutes, actually. Okay, so going back. So we have this DPC achievable region. The question is this optimal? Right? And we were able to prove a few years back that dirty paper coding, along with some other parties, that dirty paper coding actually achieves the sum rate capacity of the multiple antenna broadcast channel for an arbitrary number of transmit antennas, arbitrary number of receive antennas, and any number of receivers. Right? So this was first done for a limited case by Kyrie and Shimai in the original work, for the two-user case where there are single receive antennas. So the two receivers and an arbitrary number of transmit antennas, but just single receive antennas. And then our work was to generalize this along with Chiaffi and Yu and Biswanath and Singh. And in fact, this was only for sum rate capacity. In fact, just in the last year or so, DPC has actually been shown to achieve the entire capacity region by Weingarten, Steinberg, and Shimai. And just to give you an idea of how we prove sum capacity is, we use something called the Sato upper bound, which I'll describe in the next slide. We also used a dual characterization. So we've been talking about the downlink channel so far, but in fact there's a very close connection between the downlink and uplink channel. And the uplink channel is in fact much nicer from a mathematical standpoint. So we actually consider this dual characterization, and then we use Lagrangian duality. So I'll mention.
You want to talk about that?
Yeah, I'll mention this duality in a second, but first let me just.
It'll be useful because that's also an unused word in this field. So.
Yeah, I'll make sure I have a slide in a couple slides. So first off, let me just mention the upper bound, the Sato upper bound. So this is a picture of the capacity region. So if we just look at a two-user broadcast channel, for instance, this is the same model we saw before. H1 is a matrix here. This is the upper bound originally developed by Sato for the broadcast channel. And the idea is to consider a joint receiver of Y1 and Y2. So now if we consider these receivers sitting at a common receiver, we just have a point-to-point channel from X to Y1 and Y2. And anything achievable in this channel is, of course, an upper bound to the broadcast channel. You can only do better with cooperation than without cooperation. Of course, in a broadcast channel, Y1 decodes separately from Y2. Right? The second key idea is that in the broadcast channel, correlation between N1 and N2 does not affect capacity. Okay? For the same reason. And that is because Y1 decodes separately from Y2. Okay? What this really means is that the broadcast channel does not depend on the joint probability distribution P, Y1, Y2 given X. In the original broadcast channel, without cooperation. Yeah. It does not depend on this joint. It only depends on the marginals P of Y1 given X, P of Y2 given X. Okay? So what this allows us to do is correlate N1 and N2. Okay? So we don't change the distribution of N1 or the distribution of N2, but we just correlate N1 and N2. Originally we said they were independent, but the fact that independence is not required. Okay? Broadcast channel capacity is unaffected by any correlation between N1 and N2. And then we evaluate this upper bound. So the upper bound is the point-to-point capacity from X to the joint Y1, Y2. Okay. That upper bound is affected by correlation between N1 and N2. Okay. Certain noise correlations will give you infinite capacity even, okay. But certain other noise correlations will reduce this upper bound. Okay. And in fact, if you choose the worst case correlation between N1 and N2, you get something that's actually achievable by dirty paper coding. Okay, so this is proven using basically Lagrangian duality, showing connection between this upper bound problem for the worst case noise and something achievable for the multiple access channel. So before going on, let me mention the dual channel. So as I said, we've been talking about the downlink channel, so that's channel from X to Y1, Y2, going through these H1s and H2s. Right? So this is the channel from the base to the mobiles. And basically, if you switch all transmitters to receivers and make all receivers transmitters, so you could think of this as a TDD system, where all transmitters become receivers and vice versa. What we get is an uplink channel, right? Two transmitter uplink channel now, and the channel has just become the transpose. We get H1 transpose now and H2 transpose. So I didn't change the channel at all, but essentially the dimensions of the channels changed, right? If we had two antennas here and one antenna here, now we have one transmit antenna and two receive antennas. Okay. And then I keep additive Gaussian noise with the same power. So if it was normal 0, 1 on each antenna here, it's normal 0, 1 again on each antenna.
In what sense is this dual?
So this is dual from a TDD point of view, okay, but more importantly, this is really a theoretical formulation. And what we prove with this duality is that the capacity region of this channel, so let's say I have power constraint P on X here, the capacity region of this channel is actually exactly equal to the capacity region of this uplink channel, with power P available to be shared between X1 and X2.
Is there a geometric notion of duality like in programming?
What do you mean by geometric notion?
Well, okay, in programming I have a visualization problem, and I can, using geometry or other means, whatever you like, very precisely define what's the dual problem. Here you're using it the usual way that information theorists use it, or some information theorists have to say, the relative in the room. Right, where basically I just flip receivers to transmitters, change things to transpose because it's a dual.
Yeah.
Why?
Well, why was this channel was actually mathematically simpler, and this was kind of a natural thing to look at?
I have a suggestion.
Yes.
You should look very, very carefully some of the beautiful work of Caesar on information geometry, because you can actually make it very precise.
Okay.
And then you get all kinds of things for free. Plus, nothing like why I add noise the way I add it and so on.
Okay.
But we agree this is the usual information, I wouldn't even call it theoretic, type of duality, okay?
Okay, I'll take a look at that.
Sorry.
Okay, but this is the capacity region, or the duality relationship, is between the capacity region of this channel, and you could say this contrived channel, but this contrived channel actually does correspond well to a TDD channel. So for instance, if we have a cellular system, what that really says is the capacity of the downlink and uplink are equivalent. But there's one caveat. In the uplink, we assume there was power P to be shared between the transmitters. This may not be natural, right? Typically, you would think each mobile transmitter has its own power constraint. Okay, so if we go back a couple slides, we can actually see this duality relationship. So this picture here is in fact not drawn using the broadcast channel, because the broadcast channel leads to non-convex formulas, essentially, which don't have any nice mathematical properties. We can't optimize nicely over these things. So instead, we always deal with the multiple axis channel. We always deal with the dual multiple axis channel. And because of this equivalence, there's no difference which channel we want to deal with. Okay? And when proving this, the optimality of dirty paper coding, we do the same thing. Okay? We get this optimal upper bound, which I just talked about, and then we find the sum rate of the multiple axis channel, or the sum rate of the uplink channel, and we show that they're equal. Okay? Because of this duality relationship, that implies that the sum rate at the downlink also is equal to the optimal upper bound. Any questions about that? Okay, so basically this channel is essentially, you can't essentially do anything analytical. It's very difficult, at least, to do anything analytical with this direct downlink. Those equations I showed earlier for the dirty paper coding region don't really lend themselves to nice analytical analysis. If you took a look at what the capacity region could be described like for the uplink channel, it has some nice convex properties. And this actually, if we want to study the downlink channel, in general, I'll talk about this in a second, basically we always look at this channel, okay, because it's so much easier to study than the downlink channel.
Question.
Yeah.
This Shamai one got that's an 80-page number, right? And such it doesn't follow from such an approach.
So there's some connection. Okay, so for the sum rate we used this upper bound, the Sato upper bound, okay, where we had a cooperative receiver and we correlated the noise. For this for the full capacity region, okay, we're not just interested in sum rate. So you do something else. First, you give Y2 to receiver 1, for instance. Then you correlate, so there's, essentially you take this Y2, put it up there. You correlate the noise between these two guys, and you also correlate this noise and this noise. And then you use Lagrangian duality again. This was just to get a kind of an upper bound.
Can you show people the Lagrangian duality?
I don't have, I don't think I have.
Can you tell what is the criteria and what you adjust, what you add?
So essentially, you're able to find, if you know kind of the optimal, the sum capacity of the uplink channel, if you know the optimal power you should use in the uplink channel, you can map from that and find out, analytically determine what the worst case noise actually is. Okay. And then you can show the equivalence between the objective function for this upper bound and for the capacity achievable.
When you say Lagrangian duality,
okay, so maybe
most people will get, I have a constant add the Lagrange plus another thing, and I do that.
So no, basically, so
you should mention what
if for the uplink channel, if I want to maximize capacity of the uplink channel, I get a maximization, basically of a concave function. But instead of looking at that maximization, I can equivalently look at the dual problem, the Lagrangian dual. When there's such a thing, I can look at a different optimization in the Lagrangian space. Similarly, for the upper bound, the Sato bound, is some minimization actually, and I can look at its Lagrangian dual. Everything is convex, so the Lagrangian dual is equal to the Lagrangian dual is equal to the original problem. Okay. And there's a nice equivalence between these problems are very related.
But this is only true under this kind of model.
Yes, yes. This is not
Linear and additive Gaussian and blah blah
yeah.
blah. Okay, right? Correct or false?
Yes, correct.
Well, again, maybe I think if one uses Caesar's result, you can generalize it to different models. Right?
Okay, perhaps we have actually looked at dual problem and tried to look at discrete memoryless channels a little bit with some very limited success, but to see if there's kind of a generalization of this, if there's a more general notion of duality between the broadcast and multiple access channel, without too much success so far. But perhaps this GDAR work will let us get some more results there. Okay, so so far we've been talking about DBC. We've seen that it's optimal for some rate, and it's also been shown to be optimal for the full capacity region. Okay. But as I mentioned before, DBC requires very high complexity. To do DBC well, you want to do it over very long code lengths, which means you want to do vector quantization over very long code lengths. Okay. This is a complex operation, and finding even codes for this is not trivial. Okay. So we require these infinite length 30 paper codes. So the question then is, what is the advantage of DBC? Is it worth it to do DBC in the cellular system? Or should I just do TDMA? Or should I do SDMA, for instance? Okay, so this, for instance, let's say I have a 2-user channel. This might be the capacity, the 30 paper coding region, or the capacity region, right? And this is some capacity, perhaps. If I do TDMA, if I do very naive TDMA, all I can do is get this triangle here. I could transmit to user 1 at its point-to-point capacity, or user 2 at its point-to-point capacity, and then time share between these two modes of operation, right? So the gain is this difference here, right? So we want to measure this difference and get an idea of how big of a gain you would get from DBC. The metric we're only going to look at some capacity, okay, which is a fair metric when users have roughly equal channels in terms of SNR. It's not all, if they're very disparate in terms of SNR, it may give all of the rate or most of the rate to the best users. Okay? But if they have roughly equivalent SNRs, it's a pretty good metric for system performance. And we're going to look at a quantity we call the DBC gain, which is the ratio of the sum rate capacity achievable with DBC to the maximum sum rate you can get using TDMA. Okay. So if this is when I'm only interested in maximizing throughput of my system. I just care about the total amount of data I can output from my system. Okay. And if I'm doing TDMA, the maximum sum rate is achieved by just transmitting to the user with the largest capacity. Right? It has this nice triangular region here, which generalizes to more than 2 users. And if I'm doing TDMA, I should just communicate to the user with the best capacity. Okay. If I'm doing DBC, on the other hand, it's very rare that that's true. Normally with DBC, if I want to maximize some capacity, I simultaneously transmit to many users at the same time using this DBC, this dirty paper pre-coding technique. So we want to develop some upper bounds here to this quantity G, and then evaluate tightness and see what this DBC gain is and have some more practical scenarios. Okay, so How much time? I should try to wrap up.
Another 50 years, fine.
50
That's good.
So, in order to do,
Is there any particular reason why people use the TDMA as a base of comparison?
well, so TDMA is basically what is used right now, for instance, in HDR type systems. Right? It's kind of the most practical and it's the simplest thing to do. I'll mention in comparison to SDMA in a few slides, but we don't really know much there. It'll be really more of an open question. Right? But essentially, all systems, almost all systems that we know of today, cellular systems, wireless LAN systems, all work in point-to-point fashion. Right? You never have two users simultaneously transmitting over the same time frequency slot. Right? You do some sort of channelization either in time, frequency, codes. Right? And essentially, they give you rates like this TDMA rate. Okay, so in order to upper bound this, we're going to develop an upper bound, simple upper bound on this, and then a simple lower bound on this. Just get a simple upper bound on this DPC gain. Okay, so again, our channel H is fixed, okay, as before, and H is fixed and is known at the transmitter and receiver. And what we're able to say is that for any H and any P, let's just think of single receive antennas. The sum rate capacity is bounded by this expression here. M is the number of transmit antennas, and we basically get this H max squared is the norm of the best channel. So we have K users, we can compute a norm. Each channel is just a row vector here because we have single receive antennas. And we can compute this H max. This is essentially the best of your K channels. Okay? And this is really the capacity of a system with M spatially orthogonal users, so M spatially orthogonal channels, each of them having this channel norm, H max. Okay, I'll give a quick slide of the intuition here. So let's say we have channels, let's assume just for simplicity that they're in real space, and we have two transmit antennas, single receive antennas. Right? So H1 is each of the HIs is a 2x1 row vector, or sorry, a 1x2 row vector. So H1 is perhaps this vector here, H2 is this vector here. Okay. What we do to get this upper bound is, notice H1 has a larger channel norm than H2. What we do is just add a fictitious new user who has the same norm as H1, okay, but it's orthogonal, spatially orthogonal to H1. Okay. So this is only going to increase the capacity of my system. And in this situation, if I have, in two dimensions, if I have two orthogonal users like this, that have larger norm than the other user, I'm best off just transmitting to these two users with equal power. Essentially, I get orthogonal parallel channels now. Okay? Parallel channels with norm equal to norm of H1 and norm equal to HU. These are the same norm channels, so I should just split my power. I can do water filling, you can think of it like that, but water filling will tell me just to split my power equally between these M channels. Right? So we add, if we have more than two users, then we actually add M minus 1 channels, orthogonal channels. The result is we get M orthogonal channels, and we put power P over M on each of these channels. And the rate on each of these M channels is given by this expression. Okay, so essentially this is telling us how many dimensions we have. This is showing us that we have up to M spatial dimensions if we use dirty paper coding. Okay, now let's get a lower bound of what we can do with TDMA, and this is a very simple lower bound. If we use TDMA, I mentioned that the sum rate capacity using TDMA is just the maximum single user capacity of any out of those K users. Okay? And this is bigger than this log of 1 plus P H max squared. Okay? And the idea is that the single user capacity, or user I, is larger than this expression here. Okay? If we have single receive antennas, there's actually equality here. Right? If you have multiple transmit antennas, single receive antenna, all you do is match the channel. You basically do MRC at the transmitter, and you get this. Okay? If you have multiple receive antennas, this can actually be larger than this. Okay? This is saying to put all your power into the largest eigenmode of the channel. If you have multiple receive antennas, you should actually split it amongst the different eigenmodes using water filling. Okay? But we get this upper bound here. Okay, now we just combine these two. Basically to get that G of HP is less than M. Okay? And using a simple argument, we also get that this DPC gain is also less than K, the number of users in your system. Right? Basically, you can't do better within the broadcast than you could do if you could just talk individually to each of the users with the full channel, frequency, and time. So here, this is a result that's independent of age. This is true for all SNRs. It's also independent of the number of receive antennas here. Right? This will always be true, and this is simple using Hadamard. I've showed you the two upper bounds, and essentially those are the first upper bound is obtained just using Hadamard inequality. Right? But this is important to see that if we use DBC, all we can hope to do is get a factor of m, at most a factor of m increase. If you give me two antennas, DBC will give you at most a factor of 2 payoff. Okay? Regardless of the channel, regardless of the SNR. And now let's try to see a little bit how this DBC gain varies. So on the left here, I've just randomly picked a 10-user channel where there's 2 transmit antennas, single receive antenna. Okay. In this scenario, m is 2, k is 10, so that bound says DBC can give us at most a multiplicative factor of 2 increase. Right? And this is what that DBC gain, that G of HP, is applied as a function of SNR. Okay, what we see is that the DBC gain for very low SNR is 1, so there's no gain using DBC at low SNR. And as SNR increases to very high values, this is plotted up to 60, 70, 80 dBs, the DBC gain is actually converging to 2, which is that upper bound. Okay, but we get very slow convergence. On the right hand, I've chosen different H, but for a 10-user system with 2 receive antennas now. So I have 2 transmit antennas and 2 receive antennas. And the DBC gain doesn't have this monotonic behavior anymore. It actually increases up to some maximum at some finite moderate SNR, here about 5 dB, and then it goes down to 1 at high SNR. And we have some results about the asymptotics of G of HP. Essentially, at high SNR, the DBC gain converges to this minimum, m over n. So that's the number of transmit antennas divided by the number of receive antennas. Here we've just assumed that you have less than, or you have no more receive antennas than transmit antennas. Right? DBC gain will always be at least 1. Minimum of m over n and k. Okay? And the intuition here is that DBC is able to use this many spatial dimensions. Minimum of m, which is your number of transmit antennas, and nk. So n is the number of antennas at each receiver, k is the number of receivers. So this is the total number of aggregate receive antennas. Right? And it essentially gets to use all of those aggregate receive antennas in terms of spatial dimensions. With TDMA, you only get minimum of mn. This is the standard MIMO point-to-point expression, how many spatial dimensions you get. And this is why you get this factor of m over n. Okay? At low SNR, on the other hand, DBC gives you no gain. This G of HP goes to 1. Because at low SNR, it's just optimal to beamform to the user with the best, with the largest eigenvalue. Right? This is kind of like in MIMO too. Right?
In the previous slide,
yeah.
I didn't get to, what is the physical interpretation for the phenomenon when you have two antennas at the receiver?
So this is related to this thing here. So at high SNR, the limit will be m over n, which in that case is 1. Okay. At low SNR, it's always 1. Doesn't make a difference how many antennas you have. So this is what we see here for this scenario. At low SNR, it's 1. And at high SNR, it's also going to converge to 1.
So having more antennas at the receiver side
is bad. Yeah, exactly. So that's one thing we learned, is that if there are many receive antennas, for instance, if you have many receive antennas as transmit antennas, there's not really a large multiplicative gain to using DBC.
This is because the interference, there are interference at both antennas at the receiver side? Or?
No, this doesn't have to do with interference. This actually has to do with this dimension counting argument. Okay? What the real gain of DBC is that it gives you these extra dimensions, basically. Okay. I get this many aggregate receive antennas, right?
Because everything is independent here, right?
So there's nothing fading here, though.
But everything is independent. The noises are independent.
Yeah. But as we said,
side to side, it works, right? So
the independence of the noises.
the only thing that happens is you're going to get the increased dimensions, and that's what you get.
That's essentially, in terms of multiplicative gains, it's only the dimensions that matters. Right? So m is n, m equals n, and this is m, and this is also m. The number of dimensions is the same.
How can I get b less than 1 for the number of receivers?
No, so this is really, there should be a max of 1. This can never, I'm just assuming that n is smaller than, or less than or equal to n. Yeah, it's no more than 1. So if you have more receive antennas than transmit antennas, there really won't be any gain to DBC. It'll be very close to 1 at all SNRs. Yeah.
Is there like an intuitive explanation for that, or just this is by studying the asymptotic performance?
So basically, at high SNR, what the capacity is given by the number of dimensions times log of p. That's essentially your capacity. You don't really care what the the quality of each channel is, all you care about is how many dimensions you have, as p goes to infinity. Okay? And this is the number of dimensions you have with DBC. Okay? It's essentially like you get kind of like a co-located receiver. It's as if they're cooperating almost. Right? Let me see if this... I don't have that there. But it's essentially like you're getting co-located receiver. At ISNR, DBC